So in this video, we're going to look at question D from the section 2 of 2023. So it says high current rectification, AC to DC conversion, and inversion, which is from DC to AC, was until relatively recently achieved using a device called mercury arc valve. And it gave us a diagram. So yeah, I think I'm going to look back at these later. And then it says the principle of operation is that the mercury vapor at low pressure, 7 millipascals and 40 degrees Celsius, becomes ionized, and the ions collide with the mercury liquid, which liberates electrons. These then become available to carry the current to the carbon anode, and also via collision with atoms of mercury vapor produce mercury ions to replace those reabsorbed into the liquid phase. There is no appreciable electron emission from the carbon anode, and so the current flows in one direction only in the manner of a diode. Okay, so there is a lot of information, and yeah, let's see the first question. It says to estimate the forward bias potential of this diode. So this is essentially calculating the voltage of this entire system. So let's see, what can we use? So the diagram over here is the carbon anode, and then between let's see, so it says to calculate the forward bias potential of this diode. So the diode is essentially the entire setup. So essentially it's the mercury liquid vaporization setup, and then so basically what I'm saying is that it's this whole component over here. This is the diode, and what we want to calculate is the voltage, the forward potential of this system. And so in between, I suppose there's the liquid and the vapor, and it also gives the pressure and the temperature. So let's see. The pressure and the temperature. How do we calculate the potential in this case? Well, I suppose it's just potential is essentially defined as the amount of energy given per unit charge. So in this case, that is just the energy of each mercury molecule, right? Yeah, so mercury vapor. So mercury, I suppose, is a metal, so it's just monoatomic, and so therefore we can use 3/2 for its coefficient. So the energy will be equal to 3/2, and then you times it by PV, I suppose. And however, we've only given the pressure and the temperature. The volume, I think the volume, okay, it didn't give the volume. Then it becomes a little bit more complicated to do this. So I suppose what we can do is we can first work with the gas law, so PV is equal to RT. Now in this case, what we only know is the pressure and the temperature. We don't know the number of moles, or the volume. So, need to find a way to somehow replace the volume or the number of molecules. Well, it's per molecule, so I suppose what we can do is simply RT, right? So it's just RT, so 8.314 and then times the temperature in kelvins, so that is the temperature in kelvins. Where's the temperature? Temperature is 40 degrees Celsius, so that's 40 degrees Celsius plus 273, so that's 313 kelvins, and which gives us that's 3/2, and then you time it by 8.314 and then time 313, which gives us that's 3903, yeah. Joules. Wait, this is the energy. So essentially, what I did is that I just used R times T because essentially, voltage is just the energy given per molecule, so I just divided by N. So it's just volts in this case, yeah. So that'll be answer to the first component of the question, and then now let's see the second component of the question. So it says, inserting a grid between the anode and the mercury cathode allows the electron current to be modulated and thus an AC current produced from the DC supply. So this is essentially applying the purpose of this system. So in this case, it's converting DC current to the DC supply to AC. And it gave us a diagram, and so then it says the anode current is given by I is equal to A plus BVG plus CVG squared. Okay, so it seems that the I is oscillatory, but not necessarily using a trigonometric function, which should be rather common. And then over here it says Vg is equal to A plus B cosine of omega t. That is constant. That is a constant bias and an oscillatory signal. The anode current contains a second harmonic component, determines amplitude. A second harmonic component. What exactly does that refer to? A second harmonic component. So I suppose it's within the expression of current, there is a second harmonic component. And let's see, so one of the harmonic components should be Vg. The other one, I think, oh yeah, I believe it's that when Vg squared, you will produce cosine and also cosine squared. So cosine squared in this case is not the same oscillatory component, not that same harmonic component as cosine. So I suppose that is just the second harmonic component. So let's see, what we want to calculate is its amplitude. So it's just the coefficient of cosine squared. And let's see. What we can do first, I think, is that we can substitute Vg in first. So I is equal to A plus B cosine omega t, and then it's plus CVG squared, yeah. So CVG squared, so that will be A squared plus 2AB cosine omega t, and then plus another B squared, and then cosine squared omega t. And then if we expand this, that will give us, I don't think I need to expand the previous one, so essentially I can say dot 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 and then plus that is 2, yeah, 2b squared and then cosine squared omega t. But for cosine squared omega t, yeah, I think we need to convert this into a harmonic expression because cosine squared isn't oscillator if we look at its graph. So I think one conversion is that we can do this. So we know that cosine 2 of theta, cosine 2 theta is essentially equal to 2 cosine 2 cosine squared theta minus 1. So therefore cosine squared theta is simply equal to a half, and then cosine 2 theta plus 1. So in this case, that will be b squared. Oh wait, I did one of the coefficient wrong. This is not 2, this is c, yeah. This is c. So then what we can do is that we can substitute this into the equation. So for the coefficient of cosine 2 theta will be simply cb squared over 2 cosine 2 theta, and then plus something, and then plus something on the other side as well. So therefore the amplitude, let's say a, will be equal to cb squared over 2, and that will be answer to the question. And then let's see the third component of the question. So it says the mean value of the anode current contains a term proportional to b squared, and obtain the coefficient of this term. So a term proportional to b squared. Let's see the equation previously. So let's see a term proportional to b squared, and then what I can see is that the only possible term is just this one, and we already got its coefficient, which is cb squared over 2, and yeah, that is just the answer to the question. So let's see the coefficient. The term is just equal to cb squared over 2. So the fourth question says, if I0 is the value of I when B is equal to 0, and when the signal is applied, I oscillates between Imax and Imin. Express the ratio of the amplitudes of the second harmonic and fundamental, so that's the first harmonic, in terms of the quantity chi, which is defined as chi is equal to Imax minus Imin, Imax minus I0 over I0 minus Imin. So the idea is that we want to express the ratio of the amplitudes, and we want to express in terms of chi. So I think the first step that we need to do is express I0, Imax and Imin. So yeah, let's see. So I is equal to a plus b, I0 will be equal to a plus b, and then it's just what's left will be a plus the a squared. So yeah, that is I0, and then I think another one thing is that if we want to calculate the Imax and Imin, well, we need to express current. We need to express current as in terms of its harmonic components. So if we directly just input like cosine for example, like for I max cosine omega t is equal to 1, that doesn't necessarily work with the original equation. So I think we need to rearrange it or substitute some values into it. So initially it should be equal to a plus b cosine omega t, and then it's plus a c a squared plus 2 ab, and then cosine omega t plus b squared cosine omega t. So then it is equal to a plus ba plus bb cosine omega t plus ca squared, and then it's plus 2cab cosine omega t plus cb squared, oh this is squared, cosine squared omega t. And we need to express this somehow. And then one thing is that a plus ba plus ca squared, that's just I0, yeah, I0. And let's see, any other things? I think we can get the amplitude for the first harmonic. That will be this, yeah. Okay, and then one extra thing that we need to do is we need to convert cosine squared omega t into cosine 2 omega t. So that will be a half of cosine 2 omega t minus it's plus 1. So I suppose that's just cb squared over 2 cosine 2 omega t plus cb squared over 2. Yeah, and that will be the expression, the new expression. So let's figure out I min and I max. So I min in this case will be when cosine omega t is equal to negative 1. And in this case, that will be when I0 is equal to I0 minus, if we consider this entire term as A1 for amplitude of the fundamental of the first harmonic, then it's I0 minus A1. And then later on what we have is this component, so that's CB, so we can say is that it's just minus A2 and then plus another A2. So what's left will be I0 minus A1. And for I max, it is equal to I0 plus A1. So that is when cosine omega t is equal to 1, and then for later that is just A2 plus another A2, so that's 2A2. Okay. And then I think one other thing that we can do is that we need to somehow create chi. So that chi is equal to, let me write it over here, so I max minus I0 over I0 minus I min. And then so I max is just equal to I max minus I0 is just equal to A1 plus 2A2. And then down there we have I0 minus I min, so that is just A1, yeah. So, okay, that actually gives us that puts it in a pretty good place. And then that's 2, there's 2, A2 over A1. So therefore, your ratio A2 over A1 would be just equal to half chi minus 1. And that will be the answer to the question.